Good morning. Today we are headed into chapter 31. So this is actually our last chapter of the semester. And it's a little transition from what we've been doing. We've been looking at circuits. We're going to head back and look at what are referred to as electromagnetic waves. Now, electromagnetic waves, the word waves is a little risky here. We got to be clear about what we mean by a wave, but it's the propagation of electromagnetic fields in a way that energy is actually transferred long distance, and we call this light. So it turns out that light consists of a propagation of electromagnetic fields, and we're going to see how that is created. In particular, what we're going to find is those acceleration fields that we introduced a few chapters ago. We're going to come back and realize that when light is traveling, when electromagnetic fields are propagating through space, long distances, it's the acceleration field. So the way that we generate light, the way we generate the radiation, is through accelerating charges. So let's get started. Let's go ahead and take a look at this chapter. Now, the first thing that the chapter starts out doing is it kind of, there's some early sections that are kind of consolidating what are called Maxwell's equations. Now, through the course, what we've been doing is, when we looked at electric fields and magnetic fields, we would say, here is the direct approach, and then here are these theorems. There was Gauss's law, there was Ampere's law, and there was Faraday's law. And we said there are these theorems. This is an alternate way to look at determining electric and magnetic fields. And we've spent some time discussing that. Now, I always feel like Maxwell's equations are great. Working from these theorems are great, but I always feel like you've got to be a pretty good mathematician to really be able to stare at Maxwell's equations and just kind of solve a general type problem. It's challenging for me. There are certainly a set of problems that we've looked at using Maxwell's equations. We looked at electric fields surrounding spherical charges. Gauss's law worked really well in that case. We looked at magnetic fields surrounding wires. Ampere's law worked great. We have looked at the generation of electricity in generators. Faraday's law worked great for those situations. So we've definitely used these. But anyway, I'm gonna argue, I guess, that actually the direct approach that we've come back to, in many ways, conceptually, I think is easier to see what's going on. In any case, it's kind of traditional to say that Maxwell's equations give us a complete description of electric and magnetic fields and how they're related. Kind of a new item. So again, looking at these, I'm guessing they look kind of familiar. This was Gauss's law from chapter 22. This was this is Ampere's law from chapter 28, and this is Faraday's law from chapter 29. Now there's a new member here. This is Gauss's law being applied to magnetic fields, but there's not anything especially new here. It turns out that magnetic fields are always looping, and so when we apply Gauss's law to magnetic fields, it's always zero. So let's look at, and here it is. So now sometimes what the kind of the writing on these slides is saying, notice that the electric fields, divergent electric fields, depend on how much charge is present. Some people have suggested that there needs to be a separate magnetic charge. The charge that we've been working with in some sense applies to electric fields and we need a magnetic charge, and that's just absolutely not the case. So the reason that Gauss's law for electric fields depends on how much charge we've got and the magnetic field doesn't is because, again, the electric and magnetic field are interrelated. They're really different components of the same physical quantity, and so the way that they have been divided up, the way the components have been divided up, it was kind of intentional that the magnetic effects work out to be zero. Anyway, there's not anything missing, the theory is complete. If we did, as some people have suggested, introduce something called a magnetic charge, that would create a whole new set of formulas. It wouldn't just be a simple addition. So we only need one type of charge. That charge applies for electric and magnetic fields. The charges that we've introduced are the source for all the electric and magnetic fields. Especially when you look at special relativity, again, you can see that it's a complete description. There are no charges that are missing, there are no fields that are missing. All right, now this is Maxwell's equations the way we wrote them. So I guess I should go back and point this out too. These are written with the epsilon naughts and the mu naughts. You know, mu naught, epsilon naught, mu naught, epsilon naught. And what I've tended to do is, what I have done, is I've stuck with using the electromagnetic force constant throughout. So my feeling is, they defined epsilon naught, they defined mu naught in terms of 1 over 4 pi k and 4 pi k over c squared, and they're defined in a way where epsilon naught and mu naught is 1 over c squared. I always feel like conceptually it's easy to get confused and think that these two constants are the fundamental constants, and somehow the speed of light derives from that constant, and that's just wrong. If you think of what are the fundamental constants here, the fundamental constants are, first of all, the speed of light. And you go, really? Why is the speed of light a fundamental constant? And that's because the constant c is ever so much more than just the speed of light. The constant c tells us how the space components of space-time are connected with the time components. It tells us how to integrate space and time together. That's pretty fundamental. So c is a very fundamental constant. It tells us how many meters equal how many seconds. And then we need, since the electromagnetic force is really just one unified force, we only need one force constant. So c is telling us how space-time is put together, and k is telling us the strength of all the electric and magnetic interactions in nature. Those are the two fundamental constants. Now, why does light travel at c? And one of the predictions from special relativity is that anything with no mass, and photons, particles of light have no mass, travels at c. So it's a result of the fact that photons, particles of light, have no mass. That's why they're stuck traveling at c all the time. Any other particles with no mass would also be traveling at c. All right, a little bit of physics for c thrown in there. So here are Maxwell's equations, the way that we've written them, or the way that I've written them. And in this chapter, the first section or two, they're introducing this extra addition. I'm going to say don't worry about those first couple of sections. There's nothing in there. It's not worth the time investment to try and understand everything going in there, at least in my view. So, but the Gauss's laws, there's two Gauss's laws, one for electric fields, one for magnetic fields. And let's go ahead and do kind of an overview of Maxwell's equations and ask what they're telling us. Now, when we apply Gauss's law, what we're doing is we're asking how much divergence do we have for an electric or a magnetic field surrounding a charge. And what Gauss's law, the one that we've used, says that depending on how much charge is located here, that's going to determine how much electric field is diverging away from the charge. So we surround that volume with a Gaussian surface, and if there is charge enclosed, we'll always have E field lines that add up to some constant value, and that constant value is proportional to how much charge is there. Now, there's no such thing as diverging magnetic fields, and that's why for Gauss's law for the magnetic field, it's always zero, and that's fine. So the two Gauss's laws, we've looked at the electric field a lot, and then the second one's just saying, hey, there's no magnetic fields that are radiating away from a central source. There's no way to configure charges so that magnetic fields do that. Now, the Faraday's law. So here is Faraday's law, and what we saw this in chapter 29 not too long ago, and that says that whenever we have a region where the magnetic field is varying, that whatever has caused that effect will simultaneously create electric fields. So anything I do to vary the magnetic field will also have an effect on generating electric fields, and in particular, these are looping electric fields. So that's how we got EMFs when we were working in chapter 29. Those EMFs that would show up surrounding regions of magnetic field, those were actually due to electric fields that were being generated. And then finally, the last Maxwell's equation says that looping magnetic fields can be generated either by currents, or they can also be generated by accelerating charges. And so again, what's happening is that if we've got looping magnetic fields, it could be that the currents are generating those looping and magnetic fields, or it could be another effect of charges that have gone in, charges that are undergoing an acceleration that are creating that effect for us. So again, I always feel like people really like to talk about Maxwell's equations, but I think they're difficult. I think it's a difficult approach. Certainly examples where it's useful to work from Maxwell's equations, but I think more often than not the direct approach is easier. It's more straightforward and conceptually makes more sense. Now, in addition to Maxwell's equations, for kind of a complete description here, Maxwell's equations is only dealing with the fields. If I want to know what forces are going to be acting on charges once the fields are generated, then I have to bring in the force equation. So I want to make sure that we include the force equations to give us kind of a complete description here. All right, so here is, I'm going to put Maxwell's equations aside and just review kind of the direct approach that we've taken throughout the course. And way back in chapter 21, when we started out with electromagnetics, we said that there are electric fields that are kq over r squared, and they radiate away from a charge, and that if the charge is in motion, in addition to the electric fields, we will also get magnetic fields, and those magnetic fields are forming circular loops around the direction of velocity. Now, I've written this as C times B, and for this chapter in particular, thinking of magnetic fields as C times B is going to allow us to see a lot of the unification, a lot of the parallels between the electric and the magnetic components of the field. So this also, kq over r squared, it depends on the speed, and then it's a looping direction instead of a radial direction. Now, the key thing that we want to point out here, these are what are referred to as the velocity fields. If I have charges that are in motion, the velocity of the charge determines these fields. So whatever the velocity is at some instant, that's going to determine what the fields are, at least due to the velocity of the charge. And fields that are being determined by the charge's velocity, they drop off like 1 over r squared. Now, that's a pretty rapid drop-off in the field. When we look at the energy densities, So we had introduced energy densities in chapter 30, just recently, a day or so ago, a few days ago. Those are going to be dropping off like 1 over to the 4th power. So it's saying this, it's saying that fields propagate away from charges, but with the velocity fields, there's no net long-distance transfer of energy. And that's because the energy densities, the fields and the energy densities, they're dropping off too fast. So as I look farther and farther away from where the charges are located, I can see that the energy densities are just dropping off really fast. There's no net flow of energy long distance. In order to get energy traveling long distance, carrying energy away from a source, to get these electromagnetic fields to do that, we're relying on the acceleration fields. Now, if you read the textbook, what you're going to find is the way to describe the electric and magnetic fields this chapter, it just sounds different. They seem to have properties that they didn't used to have in the earlier chapters, and that's because they're talking about the acceleration fields, but they never say that. Anyway, we've been working with these acceleration fields for weeks now, and well, we just want to go back and take another look because they're going to be so central to everything we're discussing here in chapter 31. So the acceleration fields, electric and magnetic fields, they follow the magnitudes, follow the formula kq over r. Now that's the acceleration divided by c squared times sine theta. Now one of the important features of the acceleration fields is the electric and the magnetic field components, they have exactly the same magnitude. They're both 1 over r. They're both drop off with sine theta. So what that's saying is, and then they have interesting directions to them, at least the E fields. The E fields wrap back around the direction of acceleration. The magnetic fields they're still looping. So I got magnetic fields that are looping around the direction of acceleration. But again, the key feature here is that when we look at the fields for these, they're not dropping off so fast, and the energy densities in particular are only dropping off like 1 over r squared. And what we're going to find is that predicts that whenever charges are accelerating, there will be a net energy flow of the field away from those charges, and those are electromagnetic fields. That's light being radiated away from accelerating charges. And that's why these fields sound so different. When you read the chapter and you go, electric fields are the same magnitude? When did that happen? And let me go back and make a quick correction here. Actually, there's supposed to be a factor of c in here. I dropped it. I apologize. I'll try and get that back in the notes. There should be a c associated with that b so that we're comparing the components in a proper manner. So we're treating them as having the same units. All right, so the next slide is saying that to produce electromagnetic waves, and we got to come back, and I really have a concern about that word wave. As soon as students, or as soon as people in general, hear the word wave, they just start thinking, oh yeah, I get it, the electric and magnetic fields are kind of doing, and then they're not, right? So, and we've seen this, well anyway, we'll get to that. So we'll come back and we'll talk more about that. But what this slide says is changing electric fields produce magnetic fields and what? That's not true. Okay, you guys have your red markers? Because I think what we have to do on this slide is cross everything out. This is kind of a catchy phrase that for some reason we've gotten used to telling ourselves, and I see it all the time, and it's just not true. It's not that fields create fields, it's that it's the motion of the charges that are generating these fields. In particular, The fields that we're talking about in this chapter, the ones that travel long distance, those are being generated when charges are accelerating. So cross all this out. And instead, what we have to replace that with is the statement of accelerating charges radiate long-distance electromagnetic fields. I know that's not as catchy, but that's reality. So what they've got here is they're looking at production of electromagnetic waves. Now, one of the ways that we could have charges accelerating, one of the possible ways, would be to have current oscillating back and forth. If you think back to oscillatory motion, when there's an oscillation taking place, when charges are, oscillating back and forth, they're going to be undergoing an acceleration. So we've got a charge here that's oscillating back and forth. Now they've set up some different circuitry, which I feel like is maybe more confusing than useful. But in any case, what they're showing is that I've got, if the acceleration is in that direction, so it's not current that's the important question here, it's where is the acceleration. So if we've got an acceleration in this direction, then I'm going to have electric fields that are against that direction, and I'm going to have magnetic fields looping out of the page. So that's kind of what this picture should be showing. Now, so let's say electromagnetic waves, long-distance electromagnetic fields that are propagating are due to accelerating charges. So let's go back to our picture. Here is a charge, and here it is accelerating off in some direction. And what's going to happen is I've got these E fields that are wrapping back like this, and I got magnetic fields that are looping around. They're coming out of the page on top, they're going back in below. If instead of one charge, I have a whole series of charges, and the current is increasing. Now remember, this di dt is proportional to the acceleration of the charges. So di dt is equal to the charge per length times the acceleration. So again, it's accelerating charges, whether it's individual charges that we are thinking in terms of, or if it's a current that's accelerating. And if I have that, then I'm going to have an electric field back in this direction. Now, there's often this misunderstanding that all electromagnetic fields are oscillatory, and that's just not true either. So chapter 31 is kind of full of a lot of common misconceptions about electromagnetic fields. If, for some reason, I have a charge that just keeps accelerating in that direction, so if I have a charge accelerating, or if I have a current that just keeps increasing in that direction, I will constantly have E fields back in that direction. They're not oscillating. As long as the acceleration stays in the same direction, maybe it's a constant acceleration. A constant acceleration will produce a constant electric field in a fixed direction, and it'll produce a constant magnetic field that's looping. Now, what happens when we oscillate is that the direction of acceleration changes. So it's first of all in one direction, and then it's back in the other direction, and then it's here, and then it's back, and then it's here. And if I have an oscillating charge, then it's undergoing an acceleration. And oscillating charges radiate oscillating electric and magnetic fields. But constant acceleration charges radiate constant electric and magnetic fields. That's how it works. So again, it's not always going to be oscillating. It could just as well be a constant acceleration. Now, what we've got here in this diagram, and we're going to see something like this, different versions of this going on. If I've got at some instant an antenna, and I've got current inside the antenna, and it is accelerating in that direction, well then the E field is here. But since I know the acceleration here, it's, the charges are going to be accelerating back and forth in my antenna, and I also know that the fields are going to propagate away from that antenna at the speed of light. So what that says is, if I take a snapshot, I'm going to see an electric field here, but if I look a little ways over, I'm going to see an electric field oriented in the opposite direction. This field was generated a little while ago when the acceleration was here. And then this field was generated back when the acceleration was here. And so as the acceleration keeps changing directions, how does that work? Here, and then here, and then here, and then here, and it propagates away, what we're going to get is a pattern of reversals of the electric field at different locations, and there's your oscillating electric field. Now, these oscillating electric and magnetic fields, the magnetic fields are here too. Here they're going into the board, here they're coming out of the board, there they're going in, here they're coming out. They can be written as electric field as a function of x and t is equal to some sort of amplitude, some kind of total electric field, times the cosine kx minus omega t. I can write down the same thing for the magnetic field. All right. So that says that the strength of the electric and magnetic field varies by position. And even if I pick one position, it's going to vary in time. Because what's happening here, when we write these equations down, nothing's moving except the charges. The charges are the only thing in motion here. The fields themselves, there's nothing moving in the fields. What we're saying is, let's map out a series of locations in space. So I've got my antenna, and I'm thinking, okay, the antenna is going to be radiating electric and magnetic fields in that direction. And what I want to do is pick different locations and find out what's the orientation of the field and what's the strength of the field at each of those locations. So when we write something here, it really just applies to that one point. And I write something here, it applies to this point. And as the fields propagate away, if I stand at this location, I know that pretty soon this part of the field will pass by me. So as I stand at one location, what I'm seeing is, the electric field has a certain strength and it's in this direction, and then the field's getting weaker, and then it reverses direction, and then it gets weaker, and then it reverses direction. But that everything we're talking about only applies to that one particular point, and there's nothing at that point that's moving back. There's no motion of anything. It's just saying what the magnetic or electric field is at a certain location. Let me move on. I think we've got some other diagrams, and so looking at several of these is probably useful. So when we have an antenna, so here's an antenna, and what they're saying is when we're transmitting a signal using an antenna, maybe it's a radio station, for example, there's some kind of an AC signal. There's an alternating signal that's in the antenna, and eventually what that's doing is it's setting up oscillations of current inside the antenna. So here are the electric fields opposite. Again, they've got this listed as I, and what they really want to say there is di dt. So it's the acceleration direction, it's not necessarily the direction that the current's traveling. It's the direction of di dt. Okay. So here are the magnetic field directions, and what they're showing here is just what we talked about as the di dt, as the acceleration direction changes, and these fields propagate away. We're going to find regions where the electric field is in opposite directions. And this is just more of the same. They're saying there's an antenna. There are going to be regions where the electric field is oriented in this direction. There are going to be regions where the electric field is oriented here. And then there are going to be regions where the electric field is here. Remember, there's a right-hand rule here that says that the direction of E cross the direction of B is in the direction of velocity. So if I've got an E field that's vertical, and I got a magnetic field coming out of the board then the velocity is in that direction. So that's the reversals that we're looking at from one region to the next. Okay, here is, yeah, I've got to stand up my head to do this, but there's the E field, there's the magnetic field, and the direction of propagation is here. When we get to this is even harder. The E field is here, the magnetic field is coming out of the board right there, and the velocity direction is still off to the right. So, wave, what does wave mean here? And again, there's nothing really waving. When we talk about wave, we're really saying that something propagates outward. So one student a few years back said, oh, so what you're saying is there are wavy waves and there are non-wavy waves, and kind of. So you could have just these constant electric fields that are being generated, but you could also have fields where the strength of the field varies in a sine or cosine fashion. But there definitely is not anything doing that. It's not wavy. All right, here we go. Now that I've said that, here is the most dangerous picture, or the most useful picture. So what this is keeping track of, the red is kind of outlining different strengths of the electric field, and the blue is following the magnetic field strength, and we said that they're both the same magnitude. At least once we put in a factor of C, then the fields are the same. And again, what this is saying is, if I look at different locations in space, then the electric field varies. If I take a snapshot, these electric and magnetic fields have been generated by oscillating charges. And I can tell that from the pattern that is set up. So there's going to be a plane right here in the YZ plane, where everywhere in that plane there's an electric field that has this magnitude. And then if I step forward, everywhere in the next plane there's an electric field that has this magnitude, and then this, and this, and this. And then this whole profile moves through space. So it is analogous to mechanical waves. When we said kind of idealized mechanical waves, we generate a profile by creating some kind of a disturbance, and then that profile propagates through a medium. Now here, there's no medium. It's just the fact that we've used an oscillating charge to generate this, that we're seeing these oscillations behave in this manner. All right. In section 31.5, so I think this was, yeah, 31.4. So that stuff's good to think about. In section 31.5, they do a derivation of the existence of electromagnetic waves and their speed. And I'm going to go through this fast because I think it's difficult. I have a really hard time following these sorts of derivations based on the Maxwell equations. And again, I wonder, why didn't you just take the direct approach? If you take the direct approach, it's done. The direct approach immediately tells you how these electromagnetic fields are being generated by accelerating charges. It's just done right from the start. So it seems like an unnecessary derivation too. All right. So again, as promised, I'm just going to go through this. And while I'm going through this, I am going to tell you, don't worry about this section. All right. Now, one of the interesting features of deriving sort of the speed of propagation of the electric and magnetic fields is that when experiments, we could use experimental data to determine what speed they propagate at, and that turned out to be light. So at the time people were studying these fields, Maxwell, James Clerk Maxwell, of Maxwell's equations, was, a genius mathematician and manipulated these equations and showed that they should be once generated, they should continue to propagate through space, and was able from experiments to get an estimate to how fast, and when he saw the numbers, he realized that's what light is. Light is a propagating electromagnetic field. No surprise that the speed of propagation, c, is equal to the wavelength times the frequency. Again, get rid of the periods. This is not a causal, it's not a causality formula, it's just a relational formula. So it's saying that if I take the frequency of an electromagnetic field that's propagating, if I take its frequency and multiply by the wavelength, that's going to be equal to the velocity. Those three things are related by that equation. But they're not, nothing is causing anything there. Let's see here. The slide that we have here is looking at the electromagnetic spectrum. So what we find is that electromagnetic fields can have different wavelengths, they can have different frequencies, but more importantly, I feel, is that they have different energy. So electromagnetic fields, we now understand, consist of some number of photons. So when we say that these accelerating charges radiate electromagnetic fields, they radiate photons, particles that make up the electromagnetic field. And these photons can have different energies to them. So if we look at the chart that's provided here, what it's telling us is, well, there's a wavelength scale up here. As we go to shorter and shorter wavelength, what we find is that shorter and shorter wavelength fields have higher and higher energy. So what that says is if we get up to kind of the highest classification, gamma rays and X-rays, ultraviolets not as much, those photons, those individual photons, have enough energy that they can do serious damage. And by serious damage, if you're exposed to these really high energy photons, these individual photons have enough energy that they can take apart your chemical bonds. And I'm guessing you don't want your molecules taken apart. You don't want the atoms in the molecules dissociated from each other. That does serious biologic damage. So yeah, these photons, these gamma rays have extraordinary amounts of energy, as do the X-rays. And even the ultraviolets are dangerous. You guys know that, right? So ultraviolet photons have enough energy that they can still take apart molecules, so they can cause biologic damage. Now, once you get down into the range near visible light, and once you get into visible light, those photons have low enough energy that they're not so much of a concern. Now, when your molecules, when you're sitting out in the sun, and the UV is coming in, it's potentially taking apart some of your molecules and causing damage to your cells. But the visible light just makes your molecules vibrate. And I think that's the part we like, right? You're sitting out in the sun thinking, wow, this feels great. I like having my molecules vibrated the molecules go into an excited state of vibration. Again, it's a physics 4C topic. But when we get to these energies, that goes into vibrational energies of the molecules, but you don't want the molecules taken apart. So there's kind of a threshold a little ways into the ultraviolet where the photon energies become dangerous for us. Now, visible light, of course, is divided up. We're so partial to thinking in terms of visible light because that's what our eyes are sensitive to. So there's a visual system. There are molecules in the retinas of our eye that are able to specifically absorb certain ranges of photon energy, certain range of wavelengths. And so we have we have molecules, rhodopsin molecules, these big proteins with these visual pigment molecules embedded in the protein. And when light comes in, it reconfigures one of the bonds, protein shifts, and it fires a neuron. So these individual photons are coming in, and an individual photon can result in firing a neuron. In terms of wavelength, visible light runs from about 400 nanometers to about 700 or 750 nanometers, and very roughly, the visual receptors in your eye, there's a set of cones that pick up the blue part of the spectrum, and they are sensitive to about 400 to 500 nanometers wavelength. There's a second set of cones that are called the green cones, not because they're green, but because they preferentially absorb the green part of the spectrum. When those visual pigments are being activated, you experience the experience of green. So when photons are coming into your eye off of an object, and you go, oh, that object is green, the object isn't really intrinsically green. It's just that it radiates those photons. Or probably not even radiates, probably sunlight or room from a light is shining on it, and that object absorbs the red and blue part of the spectrum, but it reflects the green part. So whatever part of the visible spectrum objects reflect, that's what color we say they are. But it's not an intrinsic property of the object. It's just their properties of what parts of the spectrum they absorb and what they reflect. Maybe it is intrinsic in that sense. So anyway, 400 to 500 nanometers, blue, 500 to 600 nanometers, green, 600 to 700 nanometers, red. So with just really 3 different populations of visual receptor cells, we're able to experience all of the thousands or tens of thousands of different color experiences that we have. Walk into a paint store, right? How many different kinds of paint chips do they have? They got thousands. All right, so that's the visible part of the spectrum. And then there are lower energy photons. Now these should certainly be safe. At least there's no concern about taking apart our molecules unless you're exposed to too many at the same time. So infrared also feels pretty good. Again, infrared tends to be absorbed into vibrational and rotational, more vibrational quantum states, and can feel pretty good. If you have an infrared lamp shining on you, you can absorb those photons. And then getting into microwaves, like rotational energies in molecules, and then the lowest energy photons, we classify those as radio. So, and then along with the wavelengths, notice that these are logarithmic. So we're going from wavelengths of 3 picometers, 10 to the minus 12, 3 nanometers, 3 micrometers, 3 meters, 30,000 meters. And so radio energy photons could have wavelengths of, that's like 30 kilometers wavelengths for those photons. And then the frequencies, you're going from 100 up to through the 10,000, a million, so you can see how the frequencies vary also. All right, so here are a couple of examples that we will take a look at. We can work through these. So let's see, the example they have here are, let's take 60 hertz electromagnetic propagating field. Again, I'm so hesitant about calling this wave because this mental image of something wavy comes in. So I'm going to say this is a propagating electromagnetic field, and it has a frequency of 60 hertz. Now, part B says, now let's consider an FM radio signal, not a wave, it's a signal, 93.3 megahertz, and then it says let's consider light from a helium neon laser, and it's got a frequency of 4.74 10 to the 14 hertz. So it's giving you a set of frequencies. How are we going to determine what the wavelengths are? And here's kind of our diagram, I guess. So if I look along the direction that an electromagnetic field is propagating, and I look at how the field strength is varying from one location to the next, I can map out what we would consider to be one wavelength. One wavelength corresponds to the distance along which an entire cycle of electric field values is included. So that pattern is just going to be repeated as long as the oscillating, accelerating charges that generated this, as long as they keep oscillating at the same oscillation, and the oscillations here are 60 hertz, 88.5 million hertz, and 4.74 10 to the 14th hertz. As long as these charges are oscillating at those frequencies, and as long as the light is heading out, propagating at the speed of light, that says, again, we can use this relational formula that the wavelength times the frequency and the speed of light are all related by that. That gives me a way that I could go in and solve for the wavelengths. So something oscillating at 60 hertz. Now that would be all of our AC power lines, right? All of those power lines coming in from the power plant, all of the wires around our houses, all the wiring that's hidden back in the walls, that's all AC, and it's all oscillating at 60 hertz. And the wavelengths of those photons, of those electromagnetic propagating fields, is 5,000 kilometers. Okay, that's really a long wavelength, right? That's an extraordinarily long wavelength. Now, I changed the radio station from what they have. I wanted to go with a local station, so I went with KQED. Everybody listens and watches KQED, right? So if you're listening to KQED radio, they are at 88.5 megahertz on your FM dial on your radio. And again, following that same formula, it says that the wavelength is 3.39 meters. So if I'm looking at that pattern of how the electric and magnetic field varies from one location to the next, every 3.39 meters, it's a repeating pattern. Now, for visible light, and they're giving this extraordinary frequency here, again, following the formula, I'm getting 633 nanometers. Now, once you get to these really, really extraordinarily high frequencies, there's a bit of a paradox here because we can certainly we can build circuits that oscillate at 60 hertz and generate these sorts of wavelengths of kind of ultra low energy radio. We can build radio stations, clearly. KQED broadcasts at 88.5 million cycles per second. We can generate circuits that oscillate that rapidly. We can't build circuits that oscillate at 10 to the 14th hertz. So we can't build circuits that oscillate so fast that they generate visible light. Instead, the way that visible light photons get generated is when, atoms, for example, or molecules, when electrons in atoms or molecules drop from different quantum states into other quantum states, typically that's how we generate light. Now we can still show that light definitely has those wavelength properties to it. We can demonstrate that through interference effects, which we'll pick up with in Physics 4C, kind of the first topic that we look at there. But we can't actually generate, just by oscillating charges, these really, really high energy photons. So that's kind of, it's kind of like two different systems. For these, up through radio signals like these megahertz, we just generate those using signals. But for higher frequencies, we actually have to excite and de-excite different quantum states inside atoms and molecules to generate light of those wavelengths and those frequencies. All right, again, 4 or 5 different ways of looking at that. So let's say here is KQED. See, I've got frequency 88.5. Oh, I even have the KQED logo right there. So 88.5 megahertz, the wavelength 3.39 meters. What does that mean the electric and magnetic fields look like surrounding the KQED broadcast antenna, which I'm guessing is up on Sutro Tower or something in San Francisco. So here is this broadcast antenna, and we're oscillating current back and forth, and it's not a perfectly uniform sine or cosine function because we have to transmit information. So for a radio station to broadcast a signal, we have to have some way to vary the signal so that when the radio picks it up, and here's somebody with their radio, here's somebody out on Ocean Beach picking up the KQED signal, or someone at home right now listening to KQED. And what happens then is KQED has this oscillation taking place inside its antenna. Now the charges inside there, they're accelerating. They're going to generate acceleration fields, both electric and magnetic. And if we kind of set up the same pattern that we've seen, there's a lot going on here. What I did was, let's see, for the electric fields, the arrows are the electric field directions. And then the X's and the O's are the magnetic field directions. So again, the arrows up and down are showing us the orientation of the electric field. Now, if the antenna is built vertically, and we oscillate charges back and forth in a vertical antenna, that's what we're going to get in terms of the electric field orientations. The electric field is going to radiate away from that antenna in all directions, so it's going to spread out away from that antenna. And if I take a snapshot of the electric and magnetic field between where the broadcast antenna is and where the receiver antenna is, what I'm going to see is a pattern of different orientations for the electric field, right? The magnetic fields now, we said, are going to be the circles and the X's. So where the X's are, the magnetic field is going into the board, and when the O's are, the magnetic field is coming out. Into the board, out of the board, into the board, out of the board. Now this is a snapshot. So this is one instant in time. So it's like we freeze time, and that allows us to go out and map out what the electric field looks like. Let me go back to this picture very quickly. Oh, maybe not so quickly. Oh, it's back on the other side of the derivation, huh? Okay, sorry. All the way back to this. So what we've got are different strength electric fields and then different strength magnetic fields. I like their kind of color-coded look. So I wanted to go back. Okay, here we are. So this is saying what the electric field is at every location and what the magnetic field is at every location. Here's a simple, well, here's a vector diagram. The B field is here, the electric field is here, and the velocity is perpendicular. Okay. Now, if we had built the antenna tipped, that would be the orientation of the electric field. If I build it horizontal, that would be the orientation of the electric field. So the electric and the magnetic field components can be anywhere. They can be oriented in any direction, except the direction of propagation away from the antenna. So if I look at any direction leading away from the antenna, I could have some combination of, say, vertical and horizontal electric and or magnetic fields, but I can't have a component in the direction of velocity. That one's not allowed for photons. Those are referred to as two polarizations. So this is actually sort of the basis for polarization of light, another Physics 4C topic. So this is kind of a transitional chapter. It's kind of taking these electric and magnetic fields that we've been studying in Physics 4B, and we're starting to run into these different kind of quantum mechanics topics associated with electric and magnetic fields, and that's why we're talking about photons as particles that make up the electromagnetic field. Oh yeah, the wavelengths. So the wavelength would be the distance over which we see a complete set of possible orientations, and then that pattern repeats. So the idea here is KQED broadcasts, and this pattern that we've drawn is propagating through space. So what's going to happen is everything here is propagating. New sections of the electric and magnetic field are being generated. Let's follow this pattern right here, and at some point it passes by the antenna. So what happens when these fields go past the antenna? Well, if this antenna is oriented the same way that one is, the electric field components will accelerate the charges. So the electric field components are going to push the electrons and then push them in the other direction and push them in the other direction. So whatever pattern the radio station, KQED, whatever pattern they are oscillating their electrons with here as they accelerate, what that's going to do is set the electrons in the antenna in your radio with the very same pattern. If they come up with some kind of a little squiggle in terms of the acceleration, something that transmits information, then your antenna is going to pick that up. Now for a radio station, for an FM radio station, FM stands for frequency modulation. So the way they encode the information for an FM station is they vary the frequency a bit. The frequency doesn't stay right at exactly 88.5. The frequency gets a little faster or a little slower, and by varying the frequency of the radiation coming out of their antenna, that's going to set up that same very exact same pattern in your signal, in your radio, your FM radio. The circuitry in there knows how to decode that information. So they're packaging voice, right? They're packaging voice or sound information and transmitting it, and then your radio is taking those encoded patterns and recreating the sound that they had encoded at the station. So that's kind of it. That's how all of our telecommunications work, right? Our cell phones, our radio stations, our TV stations. This is kind of how anything that's wireless, our wireless internet setups, is all based on patterns set up in these propagating electric and magnetic fields. All right, here actually is an example with a cell phone antenna. So it says that a common length of antenna, an antenna needs to be 1/4 of a wavelength long. So that's a kind of a standard length of an antenna that we would need to be able to pick up signals or radiate signals within a cell phone. And they're saying that this cell phone has an 8.5 centimeter long, so it's like this, antenna. And from that, they're saying, let's estimate what the frequency would be. Well, if the antenna, the cell phone antenna, has a length of 8.50 centimeters, and the wavelength is expected to be 4 times that, that would mean that the wavelength of the microwave signal that the cell phones are using would be expected to be 34 centimeters, and that says that the frequency then would be C over lambda, and I ended up with 882 megahertz. Now, I don't really know how reliable that is. I guess I should go online and check. and see if that is kind of the range of current frequencies used for cell phone communication. I'm just not sure if that's a standard number or not, 880 megahertz. But that's kind of antenna design. How should we design an antenna so that it will efficiently be able to transfer certain frequency signals? So something in the cell phone has to be able to generate an oscillating current at 880 megahertz. All right, the text also has, it goes on and it talks about historically some of the ways that the speed of light has been measured. Now, if you go way back, this slide actually points this out. It says that the original determinations of the speed of light, this is a crazy story, but it was like in 1675. It was like 350 years ago, and it wasn't that long after, well, probably about contemporary with Newton developing, laws of motion and gravitational formulas. At that time, people had been studying the moons of Jupiter for many years. Galileo, built telescopes and is credited to be the first person who actually used telescopes to make astronomical observations. Who would have thought to look at Jupiter or Saturn or Venus with a telescope? And Galileo identified 4 moons that were orbiting Jupiter. So these orbital periods of these moons became, something that astronomers would follow. This became a big deal. Astronomers would watch the moons as they orbited Jupiter. Now, once some high-quality clocks came along where you could reliably measure the periods of those orbits, what they found was, as Jupiter was moving away from Earth, the periods of the orbits got longer for its moons, and as it was coming back towards Earth, as it was getting closer to Earth, actually, we should say it the other way around. Jupiter's moving through its orbit really slow. So as Earth was approaching Jupiter and getting closer, the periods of the orbits would get less. And at first people thought we're just imagining this, but the numbers seem to, more and more observations. And I want to say it was a Danish astronomer, I'm not sure, Romer, who figured out, maybe German, who figured out that what they could be observing was the finite propagation speed of light. Up until that time, people had done experiments, Galileo did experiments with lanterns on different mountains, trying to determine how much time it took for light to travel back and forth, and all the experiments had been inconclusive. It seemed like light just moved infinitely fast. Anyway, the astronomer Romer sat down, did some calculations, and came up with a speed of light within about 5%, 5 or 10% of today's accepted value. So pretty remarkable that the earliest measurements of the speed of light actually came from looking at the orbital periods of Jupiter's moons. Who would have guessed? Now, a person who did become very central to measurements of the speed of light was the physicist Albert Michelson, who I think was the first American physicist to win a Nobel Prize. And this was like during the probably later 1800s. Did a series of measurements at the Naval Academy. He had actually gone to the Naval Academy and done so well. He was brought back a few years later as an instructor. And if you go out along the along the Atlantic Ocean or the bay there in Annapolis, Maryland, they still have some of his experiments set up, so they can kind of show along that path out along the bay where he was doing the measurements. Anyway, Albert Michelson developed a series of different techniques. One of them was a rotating mirror, and so as the rotating 8-sided mirror, there were only certain times when this would rotate when the light would be observable in a particular direction. Now, if you take a look at this, what they've got is, this is like Southern California. It sounds like maybe, I don't know, Caltech or UCLA or something, not sure. Or if he was just doing these experiments because this site was useful. But there's a 35-kilometer distance between Mount Wilson and Mount Baldy in Southern California. And he's sending light along the 35-kilometer distance and then trying to determine how much of a delay time there is by using a rotating mirror. So a whole series of measurements that Albert Michelson did and came up with some of the first really high precision measurements. Now, this is probably, there used to be this TV show called Bonanza, and I'm guessing none of you have ever heard of this because this show was broadcast when I was a kid. But who knows, maybe on reruns. Anyway, it was kind of a cowboy show. It was a bunch of ranchers who ran a ranch, the Cartwright family, who lived on a ranch in Virginia City, Nevada. So Virginia City, Nevada, just outside Reno. It was a silver mining town, and that's where this TV show was set, supposedly in this area. On one of the episodes, and I never watched it so much when I was a kid, but actually when I was in college, I flipped the TV on, I thought, what's on? And here is this episode of Bonanza, and they have little Albert Michelson, the great American physicist, growing up in Virginia City, Nevada in the late 1800s, and I thought, that can't be right. There's no way Albert Michelson grew up in Virginia City, Nevada with the Cartwrights on this TV show, but he did. He actually grew up in, he was born in Poland. His family immigrated to the United States, and I think by the time he was, 5 or 10 years old or something, his family had settled in, of all places, Virginia City, Nevada, and even as a kid he was doing experiments in light speed measurement. So on the TV show, they actually have him out there with one of the members of the Cartwright family. Hoss Cartwright is out there, and they're on different mountaintops, kind of recreating this experiment, which eventually he would do. A few years later, in his early 30s, he was making these precision measurements. Anyway, I thought it was hilarious that on this TV show, they had this story of this famous American physicist out there on the ranch doing measurements of the speed of light. So our measurements of the speed of light now have gotten so reliable, they are so precise, that we actually use the speed of light to define the meter. Now, that's a little crazy when you think about it. So, officially, the speed of light is 299,792,458 meters exactly. Now, you're thinking, yeah, but if I'm going to use the speed of light to determine the meter, then I'm going to have the second measured very accurately too, and we do. So there's a very definite definition of what 1 second is, and it's not based on Earth's orbit. So, there's leap year, and there are seconds that get thrown into the national clock if things drift away. Anyway, but that is the definition of the meter. So the speed of light is now exactly that number because we adjusted the meter to make that work. All right, that's probably a good place to stop for the day. What we're looking at now is, we've done a lot looking at these propagating electric and magnetic fields. Again, kind of the name of all this, the name of this game is accelerating charges generate electric and magnetic fields that will continue to propagate and radiate energy over long distance. It's going to radiate light, and that light can travel as far as it wants to. In the next part, and the next time we meet and get back together, we're going to start off, we're going to go back with our energy density formulas, and we're going to try and be more, we're going to develop some more formulas. So as far as homework problems, there's a good number of problems that we'll outline in our next class meeting.